when we're talking about solutions, we're talking about making solutions, we're talking about how much we can get to dissolve. And I think most of us realize, common sense-wise, logically, that there reaches a point at which no more can dissolve. Is that right? Okay. So maybe I'm adding sugar to my iced tea. At a point I get there's no more sugar will dissolve. The sugar will sit on the bottom. Okay. Now I can stir it. I can heat it. I say when do I put sugar into iced tea? I put it in when the iced tea is warm, because the higher the temperature of the liquid, the more it will dissolve. Agreed? All right, so now let's tie in those three words. Saturated, and if I can find it, I will do a demonstration for you. Saturated means at a given temperature, as much as will dissolve. Okay? So saturated means, generally speaking, this is a little weird, and I've had people comment on this. This is why I'm going to bring this up. This is why I'm going to mention this, okay? I've had people actually comment on this. You have to have a pretty keen eye to pick this up, okay? But when we are talking about solutions chemistry, and we're talking about making solutions, and we're talking about saturations and solubilities and stuff, we did write down the solubility was the ability for something to dissolve. All right, we got that. So when I am working with saturation, and this is not a focus for our course, we're not going to do a whole thing on saturation and whatnot. You can find a lot of this stuff online, including several different simulations. I know there's a gizmo, I know there's a FET that show you how the amount of substance will dissolve varying with temperature. And generally speaking, I've said this before and I'm saying it again, generally speaking, as the temperature of the liquid goes up, the amount of solid that dissolves goes up. Generally speaking, as the temperature of the liquid goes up, the amount of gas that dissolves will go down. This is why a hot Coke goes flat. Agreed? Everybody good? Okay. So solubility, I get a kick out of it because we're working with molarity, we're learning how to do the concentrations, we figured out, if I dissolve this many moles in this many milliliters, this is my concentration. Then we took it so far as to look at the number of grams in a milliliter or milliliters, and we still said that was molarity. But then when I get to solubility, it's generally in 100 grams of H2O. Solubility is generally stated in terms of 100 grams. And I have had students pick up on that and say, well, that's not molarity, that's molality. Yeah, okay, depends on the temperature. But what we find is that if we do a graph like this, and we have 100 grams of H2O, and we are looking at grams of solute, and we have our temperature increasing as we go across this way, we generally find that our lines are going to go up like that. Now, just to give you an example, this would be something like KNO3. It gets very, very soluble as the temperature goes up. Salt, NaCl, is kind of funny. Salt starts about here. It actually starts higher than KNO3, starts higher, and it goes across like this, and it just barely goes up. At 0 degrees Celsius, or 1 degree Celsius, when it's still liquid water, I can get about 36 grams of salt to dissolve. 36 grams in 100 grams of water. At 99 degrees, not 100 because I don't want it boiling, but at 99 degrees, I can get about 39.9, maybe 40 to dissolve. So it only goes up by about 4 grams. Whereas this one starts at about 22 and goes up to about 188 in that same temperature rise. So generally speaking, most solids will increase their solubility as the temperature increases. In most cases, gases like, oh, I don't know, carbon dioxide, CO2, or oxygen will decrease. I told you the story about the fish drowning, and it's a true story, okay? But now, if I take a temperature, if I take any temperature, so like right here, boom, boom, let's call it 88 degrees. All right, so we're going to say 88 degrees Celsius. I should be able to figure out exactly how much salt, NaCl, will dissolve at that temperature. It's approximately 38.8 or something like that. I think it's all the eights that ring in my head, that's why I remember it. But it's approximately 38.8. And that 38.8 grams per 100 grams of H2O, NaCl, this would be a saturated solution. Saturated solution, meaning I can't get any more solid to dissolve, to break apart, to form electrolytes at that temperature. Now, if I need more to dissolve, if I want more to dissolve, I can raise the temperature. But the definition of saturated is the amount, the number of grams of a solute that will dissolve at a specific temperature. So how would I define supersaturated? And how do I make a supersaturated solution? And what do I possibly use a supersaturated solution for? Well, number one, I make it by taking the temperature a little bit higher, getting something to dissolve in it, and then very carefully, very slowly allowing it to cool. And if I'm careful and I don't jar it and there aren't any particles of dust or anything that get down into it and form seed crystals, I can usually keep a certain amount of substance dissolved above and beyond the saturation point. So I can start here, let's say I'm here, and let's say at 88 degrees I get, I think it's about 140 and something like that. 88 degrees C is 140 grams of KNO3 in 100 grams of H2O. All right, but now I let this cool down to here, down to about 40 degrees. Well, and I won't give you a question like this, okay, but in other circumstances, a good question would be, if I started at 88 and cooled it to 44, how much would dissolve, how much would fall out? And one of the attractive distractors, one of the answers that would frequently be put in just to throw you off would be 70. Half. Well, the temperature's half, it's got to be half has to come out. But if I read the graph here, it's actually more like, I don't know, 60 grams at this point. So what happened to this extra 80 grams? Well, if I do it right, and I have to be very patient about this, if I do it right, I can get it to stay dissolved in the liquid. And it becomes what's known as supersaturated, a supersaturated solution. I will try to find, I did this a couple of semesters ago. I had these set up at the high school, and I brought one, and I don't remember if I left it at Arundel Mills or what I did with it, but I'll see if I can find it, and if I can find it, I'll bring it in and I'll demonstrate it to you. The substance, the solute that I use is sodium acetate. And I can get so much sodium acetate to dissolve in hot liquid, in hot water, that it gets real thick and oily, and you know, when you go to pour it, it's kind of like syrupy. And if I let it cool very slowly and gently, it will stay liquidy. And then if I take what's called a seed crystal, or if I jar it, it will come out of solution. It will come out of solution and it will reform in its solid form. Okay? It's cool as hell to see it happen, because it just, you see this white crystal and it looks like this big snowflake, and all of a sudden it just goes through the whole test tube and becomes solid. And I turn the test tube upside down, nothing will come out. The second thing that happens is that there's a huge amount of heat that's released. And that's the process. You may have one of these at home, one of those reusable hot packs. Do you have one of those with the little clicker in it? The little cricket? Now, don't laugh. It's called a cricket. It used to be a little piece of metal that when you snapped it like this, it made a little chirping sound, a little, metallic chirp. In yours, do you have to put it in boiling water to get it to melt back down, or can you put it straight into the microwave?
Microwave.
Okay, so your clicker, your cricket, is no longer made out of metal, it's made out of plastic, okay? But they went from, I had these and I used them all the time. I'm always getting banged up playing soccer and stuff, so it's either hot packs or cold packs, whichever the swelling is. So I used them all the time, but the ones I had, you had to put back into boiling water. And when you put it back into boiling water, it caused all the sodium acetate to quote unquote melt and turn back into a liquid. And then it was there and ready for you to use the next time you wanted it. Click, solid heat. They came up with the idea, well, hey, if we do a plastic clicker instead of a metal clicker, we can put it in the microwave. So you can microwave it, I think it's for like 2 minutes or 3 minutes or something like that. And then it melts, it all melts down, because water in the microwave gets hot because of the vibrational energy of the molecule. But it'll melt down and then you're ready to use it again, okay? So I have somewhere a test tube with a super saturated solution of sodium acetate. And I can drop one little crystal of sodium acetate. Now, one little crystal is enough to push it over the edge and make everything come out and release heat. And I pass it around. I said, here, touch it against the inside of your forearm. It's warm. It's actually almost hot. So I was teaching chemistry down in Georgia, and I was the low man on the totem pole. When we interviewed for these jobs, they wanted to hire my wife because she was young and female and had a physics background. So they hired her like on the spot for a physics. And she was like, well, what about my husband? We're moving down here together and everything. And so they're like, oh yeah, we'll find him a job. We'll give him. So they had me teaching oceanography, okay? But then one of the chemistry teachers quit in like the middle of the year. So they said, we can find somebody to teach oceanography. We need you to step in and take chemistry. I said, okay, fine, no problem. So I was going to do the saturated solution thing, but I was actually working in different classrooms. I didn't have my own classroom. So I had 3 test tubes of this sodium acetate on my cart, and I was wheeling it to my first demonstration, and there was one of those little pieces that you put down to keep the carpets together. What do you call that in the doorway? Door jamb, I guess. And I pulled the cart over the door jamb, and as the back wheels of the cart came down, boom, like that, all 3 went, and I was like, crap, can't do the demonstration today, gotta go heat them back up, let them cool back down, that kind of thing. But it's funny how sensitive some of that stuff is, supersaturated solutions. You will see at least 1, if not 2 questions about supersaturation or about how you make a supersaturated solution. So now you have all your answers, okay? All your information. All right, so I wanted to talk about that for just a couple of seconds. Add those 3 words, supersaturated, saturated, and unsaturated. I wanted to do an example of percent composition of a compound. And this is very, very, very simple. Percent composition. Now, this is percent composition by mass. because if we have time, I'll go into percent composition by volume, which is, by the way, how your beer is sold and your wine. You know, if you've ever picked up your bottle of wine, bottle of beer, and it says 5.8%.
That's the first thing I look at.
Is it?
Yep.
Me too. And if it's 5.8, I put it back. Yeah, find me at least an 8. Somewhere there's got to be an 8 out there. You sound like a double cannon to me. Okay, we're going to talk, okay? Those loose cannons are fun and nice warm-ups, but you get me 3 or 4 double cannons, yeah, we'll play some serious cornhole.
Oh, God.
Well, I'm doing this and anyway. So by volume, if I'm looking for volume, I'm looking at what the volume of the alcohol is in the volume of the container. So if it's 5%, it's 5% of whatever 12 ounces is, which I've never bothered to calculate, but it's not enough. But if I'm looking for percent composition by mass, it's actually very, very simple. Now, I could have, and maybe in past years, I've introduced this when I taught you how to do the molecular masses. But this year I decided to save it and go back and revisit how we do molecular masses and then carry it one step further with the percent composition. So I'm going to write a composition up on the board. You should have a calculator. You should have your periodic table. You may round in here, but I'm going to ask you to tell me what the molar mass of this compound is. So let's look for a KMnO4. That's potassium permanganate. Potassium permanganate. And we said something about the manganate ion. We said that it was a transitional metal, and it actually comes in different states. And we happen to mention that manganate is the one with the most different states. It actually has 5, 2, 3, 4, 5, and 7. And we said it changes color as that oxidation state changes. Now you will be very proud of me, and now that Mark's finally here, I can go ahead and say this. On the homework that Mark just managed to pick up, and might actually get done, unlike some people.
I'm working on it.
Yeah, get back to me by Christmas, will you?
It might be done by then.
Okay, that's on 2, right? Is that 2 or 3?
What?
I do those.
Oh, okay. I cut some questions out of that. Normally you would have gotten a homework on 6, which would have been all about mass percent. It would have been about atomic formula, molar formula review.